Hello and welcome back again to the programming bootcamp. And this is the second part of the regular expressions videos. So if you just fell in this video, then it's probably better to go back to the previous video when we discussed the beginning of the regular expressions. And so let me share the screen now. Oh, and hi, Nora.
Hi.
You talked a little bit earlier, so I, yeah. Okay, so we were in this slide, and before the break. So here is this thing. We have in this example we have a bunch of strings. These just A and starting from A and then with X's in the middle. And this is the regular expression. And my question is, which one do you think will match?
Well, none of them, because there is no A at the end. Or is that not a requirement?
What I'm looking for is A and then 4 X's, right?
Right. So then the second one and the third one both should. Actually, because it's search, it's only going to find the second one. No?
So Python, it's called Quantifier limit, and it shows that these, what happened here? Yeah, okay, sorry. So
the first one wasn't a match, but the second and the third one was.
Yeah, I think I should change this and say match and print out the original string as well here. Oops.
That's a Hungarian character.
Yes,
there.
Yes, my keyboard was in Hungarian. So now, and it's even not good, that one. I have to add the F, and then I can run it. And so matching this string, and this is what the actually match was. And yeah. Matching this thing, so the third example, and this is what the actual match. Okay, so the point here that I wanted to show is that even though I said A and 4 X's, it also matched when there were 5 X's, because I didn't have in the regular expression, I didn't have a sort of something that would limit the things on the right. So what I said here, A and 4 X's, and the fact that there are more X's there, I don't care, or the regular expression doesn't care. Okay, and this is something one needs to remember when creating regular expressions with quantifiers, that the quantifiers only, that whatever the regular expression means, only that match this. Whatever's on the left-hand side and the right-hand side, the regular expression doesn't say about it anything. Soon we will set limits to this, but by default it doesn't work like this. And another programming language is actually this matching thing, the search thing, or whatever method they have. Sometimes they actually, the default is to match the whole string, because this is just looking for something somewhere inside the biggest string, and it doesn't care about the rest. Okay, this is what you asked actually earlier, that what to do with if we have a character class, how can we add the quantifier? So here is the example. You can see plus or star, the lower. So here are the examples that we are going to go through. And this is the regular expression. So it says dash, then A or B or C, and then another dash. So it will match, which one will it match?
First one, the second one, and that's it.
Yeah, so it won't match this one, it won't match this one, because there are 2, and we all explicitly said only 1. Okay, so what if I add the plus sign here?
With the plus sign, then we should get the first one, the second one, the fourth, and the fifth.
Yeah. Okay. So, and that's actually this one especially important to notice, that what we say with the quantifier is that the option to match any of these is multiplied, not that we match the exact same one multiple times. Okay. And if I replace it with a star,
it's this. Wait, the star went from 0, right?
Yes.
So then the first one, the second one, the fourth, the fifth, and the sixth.
Yes. So the difference is that the star also matches this one. Okay. Actually, I should also have an example with a question mark. So what if I had the question mark here?
So if you had the question mark, then the first one, the second one, the last one.
Yes.
Yeah.
Okay. Okay. Let's look at another example. So this is the regular expression, and this is the string. What is going to be printed here?
Yeah, sorry. Then the whole string would be printed there, right? No, just the thing that it matched. So it's okay. XA.
How many A's?
Oh, any A's. Okay, so X and 3 A's.
Right. Okay. So what if I have the same regular expression when this is the expression? Okay, so wait a second. Before we go again. So you actually first said XA and then change it to X.
Yes.
So theoretically, either one could be, okay, because both match the definition of X and 0 or more A's. But the quantifiers are greedy. That's sort of the title, right? So if they can match more, then they will match more.
Right.
Okay, so now that you know this, what will happen in this second case?
Then I suppose it will say XAA. No, because so the search method only finds the first one, right?
Exactly, exactly.
Okay, then it will say XA.
Okay, so it's not just greedy, it's also what we call eager. So the first one that it matches, it tries to enlarge it, but it won't go and look for another one, even if it might be bigger.
Okay.
Okay, so that's why it matches this X and A. Okay, so now let's say, now that you know this, what this regular expression matches in this string. So now we change the regular expression.
It would still only say A, right?
Almost.
Because that's the first one that it finds.
What does A star mean?
Any number of A's.
What is the any?
From 0 to. Aha. So an empty string.
Exactly.
Or, okay.
So before the X here, it's a little hard to see, but there is no A. Okay.
That's true.
So it's 0A. And because the A star doesn't have anything to directly that enforces it to match anything, so it will start here before the X and it will match nothing, or the empty string actually. Okay.
So here we should most probably use the plus instead of the star if we actually wanted to get an A back.
Right. So this is basically quite meaningless, this A star alone, because it just means that match some A's or not, which is like a really empty sentence. I'm showing it especially because of this. So this, to understand these small things and of course not trying not to fall in these traps. So now, okay, if I have this A star and all these,
then it will find AAA, like 3 A's.
These 3 A's, right? Okay, let's see if that really works. Right. Okay, so the XA, the empty string here, and then the 3 A's.
Yeah. Okay.
Good. So as opposed to being greedy, we can also tell the regular expression that the specific quantifier to have a minimal match. Okay, so when there is a choice, it will try to match as little as possible. That's basically what it says. And the way to do it is rather confusing, is to add a question mark after the quantifier. So this is not the 0-1 quantifier. This is something that changes the meaning of the star. Okay, and you could also add it after a plus sign, changing the meaning of the plus sign, or a curly brace. And actually there is an open price, I think still, for someone to create a regular expression that's actually useful, that has the question mark, two question marks, one after. So making the question mark itself non-greedy or minimal. But probably there is no real reason to do that. Anyway, so this one says, okay, A dot star B. So match as many characters as possible. So in this case, A, and then it will match up till this B, right? Okay. So this will match, what will this match?
So that should match, we're looking for the minimum one, right?
Possible anything here.
So that would be AXB.
Right, so it will match only this part.
Yeah.
From the same string. Okay.
Yeah.
Now, what's important here is to understand how the regular expression engine works. So what it does is takes A, matches the A, great, then goes to dot star matches everything, okay? I mean, the regular expression doesn't look much further. So it matches everything, including this B, okay? And then it says, the regular expression notices, oh, I also need to match a B. So it goes back, what do we call backtracking, to the previous decision when it decided to match everything. And then it removes the last character from the match. So then the dot star will match everything except of the last B. And then this B can match. Okay? And this will work the opposite way. So first A matches A, then dot star question mark matches nothing because that's the least that it can match. And then the B tries to match, but it says, no, there is an X, there's an X, okay? So then the dot star question mark will start matching one element. And then the B matches and we are done, okay? And that's especially important here. So what will be the match if it's this regular expression and this string?
So it should be from the first A. Oh, actually, there's only one B. So
yeah, I see, yeah.
From A to B.
Yeah, I just noticed it. Maybe it's a mistake, I don't know. So it's from A to B, yeah.
Yeah,
okay.
So only the Q remains.
Yeah, maybe there's a B missing from this example, actually. So what will happen here?
It will go until the first. Actually, the B is now before the number, so it will only go until AXYB.
Yeah. Right. Yeah. Okay. So the D's are here. Okay. So why is this interesting? I mean, in both cases, both regular expression will match the exact same thing, but in this case, this will be relatively fast. Because this will, the matching everything is fast, and then it only has to backtrack once or twice, and it's done. But if I used this regular expression on this one, it would work a lot more. Now, this is still a small example with only 10 characters,
right.
But when you have a huge regular expression, this might also be relevant, okay? And the opposite here, speed-wise. Okay, anchors. Okay, anchors are tools in regular expression that can match a location, but they don't match a specific character. And there are a couple of these anchors. One of the popular ones are the caret and the $sign. But the recommended, the similar tools, but the recommended ones are the \A and the \Z, the capital ones. But most people will use the caret and the $, because they are older, and that's what people get used to, I think. But they are sort of less correct in a way, okay? So what the caret means is to match at the beginning of the current row. And I'm sorry, if the caret is at the beginning of the regular expression, then it means to match the beginning of the row. If it's at the end of the regular expression, it means to match the end of the row. I could also say end of the string, because usually you work line by line. that each string that you work on is one line, one string. But if there are embedded new lines in the string, then it makes a difference. Then these two are going to, so if there's, okay, let me try to say it again. So if the string is a single string without new lines in it, then the \a and the caret behaves the same. And also the \z and the dollar behave the same. But if there are embedded new lines, then the behavior might be different. Okay? And in order to make it different, you also have to provide this this parameter option to the regular expression. We'll see that in a little bit later. So how can we use this? If we have this regular expression, this means to find a cat anywhere in the text. If I have this regular expression, it means that the text has to start with the word cat. And if I have this regular expression, then it means the string has to end with the cat. Okay, cat. Okay, and the same is this. So this starts with cat, and this ends with cat. Okay, and I myself almost always use the caret and the dollar sign, even though I should know better and I should use the \a and \z, but that's just because I'm so used to it. Okay, so if you go over the example, so this cat will match this one, and this one. This cat will only match this line. The same here. And the cat with the dollar at the end will match this one only. And the same with the cat with the \z. Okay? And okay, and yeah. And then you can also put actually this caret and dollar or \a and \z, you can put on both ends. And then basically your regular expression describes from the beginning till the end the string. Still inside it might be flexible. Okay, right now it says digits. Okay, here it also said digits, one or more digits. And of course it could be a lot more flexible, a lot of other things can be there. But it describes the whole string. Okay, and here we also say there are digits. So the first one will match digits, okay? And it won't match here because we are expecting at least one. And this one will only match where it begins with digits. And this one will, where it begins and ends with digits. Okay, maybe I should add examples when we start with digits and we don't end, so we can see it more clearly. Okay, so these are the main examples, and then there is another one, another anchor, which is called \b, which stands for, I don't know why it's \b, but it matches any end of word or beginning of the word. I said here edge of word. Okay, so what is the end of a word or the beginning of a word? When one sign is a word character, so something that's in the \w, and the other sign is not. So the not part can be either another character that's not in \w, or the beginning or the end of the string. Yeah, it's rarely used actually.
Yeah, that sounds a bit confusing.
Yeah, it's confusing and it's actually rarely used. I'm showing it, don't worry about, of course you don't have to remember any of these. You start playing with it, start using it, and then slowly start remembering these things. So just to have the example, so here this is this just random string, and I ran on it, so dot, \b dot, meaning any character, a \b and any other character. And what it matches is X space, because X is a word character, the space is not. And here A space and B space and X dash. Okay, but it, for example, it didn't match the R, the underscore, because they are both in \w, but it does match the underscore space. Okay, and T exclamation mark, because T is a \w and the exclamation mark is not. So that's basically what it shows. And there are a couple of these examples. So here we have end of word and then any character. And it matches, so this is the string, it matches A. Okay, so here the end of word was, okay, beginning of word. So just before the A. Okay, first.
Sorry. No. Can we go back to that UT bit?
Yeah, first of all, this one, right? You notice the two dots. So it all the \b. The \b doesn't match anything. It's just a location. So every time you see two characters here.
Yeah.
Okay.
Okay. Right. Okay. So it's always two characters, right?
Yeah. So it's only used to align a location, not to match any specific character.
Right.
Okay. And here, because of that, here in this agregal expression, we only have one dot, so it will only match one character. But the character must be immediately after an end of word. So whatever is before that must be different from in its wordiness, okay, than what we match with the dot.
Right.
So if we are matching the letter A here, then whatever is before must be a non-word character or nothing. Okay, because the \b also matches where the string or the whole string starts.
Right. So if we were matching an X, then the first X would actually come up from the text.
Sorry, if we're matching.
So if we were looking for an X, the letter X.
Letter A. Okay.
X.
X, yes.
Then the very first X in the text that would appear, right? Because that's before that is the edge of the string.
That we are looking on this one, so it's not on that string.
Right. But if we were looking on that one.
So let me change it and tell me how to change it, and I can figure it out.
Oh no, nothing. Okay, I understand now. I misunderstood something.
So let's show the example.
Okay.
Also wanted. So I was just thinking.
No. It was just so that the A is found because before it there is nothing. That's the edge of the string.
Yeah, because there is no. So there are two reasons to find a character. So the B, okay, let's try with the B. So the B here, the B is found because the character before, because B is itself a word character, but the character before is a space, which is a non-word character.
Yes.
And the space here is found because the space itself is a non-word character, and the character before is A, which is a word character. So there is the edge between them.
Right.
And the A is found here, if you're going backwards, because it is a non-word character and there is nothing before it. Okay?
Okay.
And in the second example, okay, we have .b. So here the .b, maybe I should replace it with not the letter B. So that's confusing. Okay, so the letter B is matched because there itself is a word character, and afterwards there is a non-word character. So the dot matches the B. The space is matched because it's not a word character, but afterward there is this letter B, which is a word character. And now this the A is matched, okay, because it itself a word character, and afterwards there is a space. But in this example, and that's the difference between the two, the last space is not matched because the space is a non-word character, and afterwards there is the end of string. So the \b would match, so it matched here. It matched here before because it was a word character and the end of the string. But if it's a non-word and then the end of the string, then it doesn't match. Okay. So rather extreme cases, but we'll have an example where it's actually useful, the \b. Okay. So anyone, if is not completely understanding the \b thing, don't worry. Really, I'm trying to show various examples, and then later on we'll see some usefulness of some of these. Okay, so do you know what an ISBN number is?
Yes, it's for banking, right? For international.
No.
ISBN.
That's another.
IBAN, right? That's a different one.
Different one.
ISBN, that's for books.
Yes.
Yeah.
That's International Standard Book Numbering.
Oh, okay.
Okay. There are like 3 or 4, but it's standard. Okay. So it's basically, I haven't fully read the documentation or whatever. It's basically a number that looks like this. Okay. And sometimes I notice that there can be an X, a capital X, but I think and then there are several sets of these with different lengths. But I don't want to worry about it. So what I wanted to create here is just a regular expression that can match, get and decide if a given string is a proper ISBN number or not, properly formatted. Okay. And as I said, there are all various lengths of ISBN numbers because of the, I don't know, it was changed, I guess. But so let's assume here that we need 13, that it must be 13 character long. Okay, so not the other ones. So here are a bunch of examples, okay, and a regular expression that can match it. So I go, okay, let's go with the simple one. It says it has digits, okay. It can have digits and capital X and dashes, and 13 of them, and they must be from the beginning till the end. Okay, and yes, I should add now the re.ascii. Now that I've also learned that the \d matches all kind of other letters as well. Okay. So in Python 2, you didn't need, in Python 3, you need this. Okay, so this is sort of good. It matches all of these. The problem that it also matches this and this, which are clearly not good ISBN numbers. So it was a really easy to create regular expression. And it can filter out a lot of bad things, but not everything. Okay, so I said, okay, let's create a more complex one. So basically, I went and read a little bit more about the ISBN numbers and said, okay, the first part must be between 1 and 5 digits. The second part is between, and then there is a dash. Then \d between 1 and 7 digits. Okay, then a dash, then digits between 1 and 5 digits, okay, then a dash, and then it can have an additional either a digit or an X. Okay, and I really don't know if this is really true or not. I'm just more or less making it up. The problem is this. So this is a much better description of it. And now I had the caret and the $sign, so not to match just the middle of something. So this is good, but it unfortunately can also match cases when we have only 1 digit, 1 digit, 1 digit, and 1 digit. So I still need to make sure that it's 13 character long, but I don't need a regular expression for that. I just can use len, right? And in reality, I will actually swap the two around. So the checking the length would be the first thing, and only then the regular expression, because checking the length of something is probably an order of magnitude faster than running the regular expression on it. So I would filter out all the incorrect lengths first, and then the regular. Remember the short circuit?
Short circuit.
Yeah. Okay. So
no.
No. Okay. So how in a Boolean expression, if you have something and something else, then if the first, it will be true only if both of them are true. So if the first one is false, then I have no point of checking the second one.
Right.
Because I already know the end result.
Yeah.
So that's why it would be important to swap them around. Because then if this is false, if that's the first one, then the regular expression is not even checked anymore. So we save that time.
Yeah.
Okay. So this should be actually in the opposite order in order to, it might not be a huge saving of time, but generally these small things, when you can pay attention for this, then it's worth it. There's no, it's not less meaningful, the code. Even it might be even more meaningful that we first check the lengths or clearer. Okay, so, but now we already actually read here a regular expression that was like 15 characters long. So it's not that bad at the end. At first sight, this, I mean, if someone comes and looks at this without the previous hour and a half discussion, then it's really horrible. After an hour and a half, is less horrible. Okay, but you can go. It needs a practice. Okay. So let's try this one. Here we have a long string, and we have these sections like starting, ending. Okay, and another one, start, end. So between the less than and the greater than side, we have some text. And we would like to match that text. So we said, okay, let's match less than, and then some characters, and greater than. So what will this match?
So it should match a string.
So far, it's good.
But then, how do you make sure that it stops after the string and it doesn't go to the end of marked?
Right. So as it is now,
it will only find a string.
It will match the whole thing.
Oh, okay.
Okay.
Because it's greedy.
Because it's greedy. So what will actually happen is that this will match the first less than sign, then the dot star will match till the end of the string.
Right, and then go back.
And then slowly we'll backtrack until this point. And at this point it will say, okay, I'm fine, done. So how can you tell it that? So then that's the question. How can you enforce or make it match only this part?
Well, you can't use the $sign because that would still find the marked one. Oh, you can use the question mark to make it minimal after the start.
Right. So this is one of the solutions. Okay, just put the question mark after it. And then it will start, then the engine will work, okay, match this one. Then this won't match anything. And then slowly it will grow till it matches the S string.
Yeah.
And then the greater than sign will match here. Okay, so that's one solution. But there's another solution which is, I think, actually better, at least faster, maybe clearer, I don't know. And this other solution is to use a negated class. Okay, saying, okay, so I match a less than sign, then any character which is not a greater than sign, and star. So now, instead of doing this backtracking and slowly taking more and more characters, the regular expression engine can just actually run ahead and say, okay, I match this first, and then run ahead till this. Because,
right.
Okay, so it won't need to this, oh, let me check another option and so on. Okay, and again, maybe in this such a small example where you have a single place of a single quantifier that can have a lot of backtracking, maybe that's not meaningful. But once you have a larger regular expression with several quantifiers and several places where decision must be made, then actually a regular expression can be extremely slow. With some thought, you can actually make it faster. Okay, so that's now I'm not want to bore you about this slowness. I mean, it's still blazing fast usually. Okay, but there are these horror stories when one regular expression with some particular input took so much time that well, it was bad. Okay, so we have one of the things that we talked about or mentioned is that the dot matches anything except new line, and that you can provide options to the regular expression engines. So one of them is the re.all option. So this is how you would do it. You run search, regular expression, the thing that you are searching on, and then an option or multiple options you can put there. So this will change the behavior of dot. In the first line, I have just a single line without a new line. The second one is a multi-line string with the triple quote. So there are the new lines here that sort of are invisible, but we can see them because the text is on the next line. So if I run search like this on line and on text, so what does it match? This.
So the first one will go from the beginning to the end of, the bigger than, smaller than signs.
And this
and then
one?
In the next one, it doesn't consider new lines here. So it will just find it will get nothing, right?
Exactly.
Or, yeah.
Exactly. It won't match anything because the div starts matching, and then the dot star cannot match anything else because because it can't match new lines. Okay. So here is where it's important, because now if I give re.all, okay, then it still matches because
the same
there are no
thing,
new lines, so there's no impact. And here it matches the whole section here.
Yeah.
Okay. And how do you get text like this? If you, from a file, you use fh, so file handler .read, then you would read in a file with all the new lines inside.
Right.
And just think about, you have some text that actually, that some section starts from on some line, and then you have some content that ends on some other line. And if you do it line by line, it's gonna be difficult to notice this. If you read the whole thing in and then use the .all, then it's gonna be much easier.
Right.
To match and find. Okay. Again, this is not very often used, I think, but when you need it, that's very useful. Another option is called re multiline. That changes the behavior of caret and $. So you remember they had the \a and caret, they were the same, but when you give the multiline, then the caret changes its behavior and the \a remains. So now if you give multiline, then the caret will match the beginning of a row, not the beginning of the line. And again, here, there is only one row. So one row and the string is the same. In this, we have 1, 2, 3, 4, 5, actually 6, because there is a 6th one here, I think. There are actually 6 or maybe even 7 rows, I don't know, whatever. But only one string. So \a would still only match here, and \z only match here. But the caret can match here and here and here and here and here, all these places. And the $, can match here and here and here and here and here. Okay, so when I try to match start and okay, so this is a funny thing. Yeah, what does this match?
So that matches a digit or a non-digit.
So
anything.
Anything.
Two anythings.
Yeah, no, it's just, yeah.
Oh, just anything.
Just
yeah,
anything. Just anything.
One anything,
okay?
Yeah.
So some people use this instead of dot because this matches really everything except even new line.
Right, okay.
Okay. And the reason I used it is because I didn't want to use the both modifiers in this example. Probably
right.
Just mixing up people. So anyway, the point is that this multiline allows us to match the beginning and the end of a string of a line or a row inside a text. And again, this is also only useful when the text has multiple lines. Okay, shall we look at it?
So if that goes, then it only matches the end of the string, the string, not the lines, right?
Mm-hmm.
So then in line, it would just match the whole string.
So in this case will work, right?
Yes.
And this case won't work.
Because it doesn't consider new lines.
Because this matches the new lines. That's not the problem. The problem, the caret only matches at the beginning of the string.
Right.
Here.
Right.
Okay. But when we modify it with the multiline, actually here it doesn't matter because it's a line.
It's the
here
same, yeah.
Because we modify the behavior of the caret.
Yeah.
Now the caret will also be able to match here.
Right.
Okay, so if we run this called multiline, okay, so above so here first it matches only the line, and below this whatever the mark, it matches both.
Right.
Okay.
So what would \A do then?
So \A would only match here.
Right.
Okay.
So it would do the same thing as the caret in without the multiline.
Yeah, exactly. So if you don't have the multiline, then the caret and the \A behave the same. Okay. And that's the reason most people actually use the caret, even though they should use the \A for that. But
right.
Okay. Okay. What time is it? Still have some time, right?
Of course.
Okay. So what if we have, okay, this is a good. So if we have these strings, and I would like to find any case where there is either apple pie or banana pie. And the easy solution is to create two regular expressions. To search for apple pie, then to search for banana pie, and then we have two matches, and then check if this or the other one matches. Okay, and well, I don't even need these variables if I don't really need them, but so that's the easy thing. And that's easy for this case because we have only one like or condition. But if we are in a bigger regular expression where it's also there, you also have a part that can be either this or that, then we need something else, okay? And the character classes, they also provide some or, but they are only for single characters. And here we have longer ones, longer strings. So that's where the pipe comes in. This is another operator or tool in the regular expression language, which just says either apple pie or banana pie, okay? So this will match exactly the same that the two regular expressions matched earlier. And you can notice that, well, there is something common here. They both have space pie at the end, okay? So we can, just as in mathematics, move them out of the parentheses, basically. So this is what the replacement. And you need to put the parentheses here, because if you don't, then you would be saying apple or banana pie, which is different. We wanted to say either apple or banana and then space and pie. Okay, so now we have this either or, but how can we know which one it's actually? Was it apple or was it banana?
I mean, if you call group on it, then you
right. Yeah. So it's even though I didn't originally wanted to use that for that, so I used it because of limiting the the pipeline, but it's also capturing whatever is inside. So the
Right.
group one will contain the word either apple or banana. Okay, so now we get to this funny thing. How can you match something that has two characters, the same character, one after the other? So let's say as in apple, you have two P's, and in loop, you have two O's. You don't know upfront what character you're looking for. You just want to have the same twice. And for that, the regular expressions have something which I call an internal variable that look like this: \1, \2, \3. So they are numbered. And the way they behave is that if you have a pair of parentheses, then as the engine works, as the regular expression engine works, the pair of parentheses capture something that hopefully will be part of the match. Maybe not, maybe they have to replace it, but for now they assume that, okay, assume we match this one. And then they put this value into the variable \1. And then later on, in the same regular expression, you can use the \1 as meaning that match the same thing that was already matched. So here, the way this works on banana is that the dot matches B. So then B is the value of \1. So the next thing that we would like to match now is the letter B, but it's A. Okay, so that can't work. So we backtrack, go back to the previous decision, and then dot will try to match the next character, which is A, and put the A into the \1. And then it will try to match A, but it's an N. And so on, and it will reach the end of the banana, and it will say, okay, I didn't find anything that can match the whole regular expression. On the other hand, when you're doing this apple, so first this will match A, put A in the \1, but the next character is not A, so it doesn't match. So now it backtracks, it tries to match something else with the dot, the letter P, puts the P in the \1, and then, oh, it's the same letter. And now we reach the end of the regular expression, so we have a match, and that's it. Okay, so where is this letter? It's in group 1. So these \1, \2, \3 are actually the same things as the group 1, group 2, and so on after the match. So this is the location where the regular expression actually is collecting all these values, so they will be available for us later after the regular expression is matching. Okay?
Yeah. Yeah.
Okay. It's a little bit like recursive things, no? So you're using something that you don't have it yet. You don't have
it.
Right. But it's just a variable. You just don't see the assignment.
Yeah.
Sometimes they also call it a buffer, but it doesn't really matter. Okay, so let's try this one. Now, do you know any, what is it called? Group, a band that would match this?
Oh my God.
It's very,
so,
I mean, your parents know.
I'm sure. I need to first decipher it.
Okay.
So this would match. That's anything, and then that put. So this is so confusing.
Okay. So this.
I don't know.
This will match. Okay. So let's read it.
Yeah.
This will match a character, any character.
Yeah.
Okay. This will match another any character. Okay. But this will be in \1.
Right.
The first, and this is going to be in \2.
Oh, right. ABBA.
Oh, right. Oh, that's easy.
Yeah, I just need to understand what it's about. But now, yeah, I get it.
Okay.
Okay.
so this is just the first, this is the second, and then I will say, okay, so match the whatever the second one matched, and then whatever the first matched. Okay,
right.
that can be pretty powerful. So let's try this one. What does this?
Okay, does it only work with dots?
No.
So anything that we match first goes into.
Yeah, anything this captures goes into \1. Anything the second pair captures goes into \2, and so on.
Right. So that's a digit, 2 digits, and that goes into the \1.
Right.
And then any number of anything else.
Yes.
And then the same 2 digits at the end.
Exactly.
Okay.
So it's some 2-digit number, some garbage that can actually be also empty, right? Because it's dot star. And then the same 2 digits again.
Right.
Okay. And this one?
So that's 2 digits, anything after that, then the same 2 digits, then anything after that, then the same 2 digits.
Exactly. Okay. So now basically some 2-digit thing 3 times.
Yeah.
And you don't care what's inside, in between. Okay. So what is this?
So that's 5 anythings.
Right. This is 5 anything. This is the loop.
Yes. So 5 anything, then any number of anything, then the same 5 anything again.
Yeah. So the same thing that we code here again.
Yeah.
So this is a string that has a 5 long substring repeated.
Right.
Now limit it for DNA and you are done, right?
Yeah, that's actually helpful.
Okay. So that's the next slide, okay? So here are our friends. So 4 characters, and here I'm just generating a random DNA, okay? So basically from 0 till 100, 99, pick up one of the letters and add it to the DNA string. So it's a 100 long DNA sequence, okay? And what I would like to do is find the longest repeated sequence in it. Okay, and I guess you would use a normal DNA. I just wanted to create something here. So this is now going to be funny or fun or what. So basically this is a regular expression you would like to use. So let's say I would like to check if there is a three character long substring that's repeated. So this is the regular expression for it. So it says any of the 4 3 times, and then this goes into \1, right? And then dot star means anything, and then \1. Okay, so this regular expression would match if there is a 3 long substring, okay, subsequence or whatever sequence that repeats itself.
But only repeats itself once.
Yeah, but that's
it's enough for the repetition.
No, I don't care about the number of repetitions. I care to find the longest repeated sequence. I only want it once repeated, but I would like to find the longest one. Okay. So what I thought, maybe there is better solution, is to start running from 1 and try this one. If this matches, good. Then try the next one. If this matches, good. And if I found, let's say, that this one doesn't match, then I know that the one that matched last is the longest one.
Right.
So I try first, okay? Maybe there's a better way to do this, but this is what I found. So I need to have a loop going over all the lengths. I mean, these are all the same regular expressions, just the number is different here. So what I'm going to do first is build the regular expression on the fly. The regular expression at the end is just a string itself. It just has its special meanings, okay, for the engine. So this is how it looks like. as the beginning part of it, right? Then I create from the current length. Okay, so I have this variable length that has 1, and I'm going to increase it all the time. So from that, I add this number here, whatever is in, and then add the end of it. So this variable now actually contains one of these, depending on the length. So in this loop, I go like while true, okay, as long as it takes. I create the regular expression that looks like here, using the current length, which is starting with 1. I run the Regex engine on the DNA, get the match. If it matches, right, then I save the current result to some variable called result and increase the length. And then try it again and again. And then once it fails, I break. And then I know that the result contains the longest substring that's repeated. Okay? I don't know. I came up with this example long time ago because I found it interesting and I don't know how useful these things can be. But I wanted to show also that it's not you can build your regular expressions on the fly. I mean, put them together and then it's just a string. Okay?
Yeah.
Okay, so there is this ignore case parameter that just ignores the case. So, okay, I mean, not very useful. Okay, rarely needed. This is actually a very important one, the verbose. So you can also put RE verbose there as a parameter, as an option. And that allows you to break up your regular expression into multiple lines. And to put comments in your regular expression. Without this RE verbose, every character that you have in the regular expression has a meaning. If there is a space in the regular expression, it matches a space. If there is a hash mark, it matches a hash mark. Okay? But if you give it RE verbose, then it means that none of the spaces have any meaning. They are just there, okay, for readability. And none of the new lines, and none of the hash marks, and nothing after the hash mark. Okay. This also means that if you actually want to match a hash mark, then you will have to escape the hash mark, okay, or do something special. So there is some limitation, but having this regular expression, well, it's not that complex to read it. But if you broke it up like this, and you even put some comment on what is this part, okay? So if you put here, okay, so if here you will put match word characters, then that wouldn't be a good explanation, okay? Because if someone doesn't understand that \w matches word characters, then probably they shouldn't deal with this. They should first read this, what are these operators? But the meaning of this whole section is that the username, okay? And then the @mark, and then this is the domain, and this is what we call the GTLD. So this is basically matching an email address. Okay, it's a very simplistic version or simplified version of matching an email address, and it obviously won't match a lot. Just the concept of the fact that you can use this verbose, also called sometimes extended, but doesn't matter. And then you can put in these comments and align nicely, and so you can make it much more readable. It's important, especially if you have some complex regular expression.
Can you use a pre-existing list? Say it's a list of all of the GTLDs. Would you be able to put that in a regular expression in any way?
So what can we put in a regular? It's a string, right?
It's a string, yeah.
So what can you put in a string?
I mean,
with an F.
Oh, right. So you can actually refer to it the same way we did before, right?
Yeah,
right.
we put a number there.
Yes, yes.
So
Okay.
if you can, you've converted it into a string with the str, but put in a number. If you have a list, you need probably to join it together.
Yeah.
Right.
Join it together with the pipe
Maybe.
characters. Yeah. Okay.
Right. Okay. Good.
Okay.
It's good that you're asking because we are going to need it soon.
Ah, okay.
So far was the regular expression part. Okay. And now we have a couple of slides with the search and replace part, so substitution, which is called substitution in this case. So here we have, so how does it work? You use re.sub, give it a regular expression, just as we learned so far, it has to match something or can match something. Then you give it what to replace whatever the thing matched, and then what you work on. And this won't change line, it will return the changed string, the updated string. Okay, so the original string will remain intact because it's immutable. Okay, so in this example, we have this string ABC123DEF, and we match digits. So in our case, it will match the 3 digits in the middle. And I'm replacing that with a single space. So the result is ABC space DEF. This is what, if I assigned it to something, that's what I would get. Okay, what if I have this substitution, X instead of space Y? So, wait a second, what's going on here? Yeah, okay, sure.
So you're looking for an X.
Yeah, but there's no X.
Then there is no X.
So nothing happens. Okay, that's just was the whole point here. So the thing is that it won't break anything if you just try to replace. So you said, okay, just replace anything that matches this. If there was no, then okay, nothing happened. Okay, okay. So what is this regular expression?
So it's a letter from A to Z.
Okay.
Or any letter from A to Z that is more than 1.
Okay.
Any number of letters that goes into \1.
Okay.
Then any number of digits that's more than 1, okay. 1 or more.
Yeah.
And then that goes into \2. And then that's actually the same thing as before.
Yeah.
But it's not the exact same thing. It's a new any number of.
Yeah. Okay. So,
any number of characters.
Yeah. In our case, this will match ABC.
Yeah.
The middle one will be 1, 2, through, and the other one the last one will be a DEF. But we can use this \1, 2, 3 also in the substitution part.
Right. So then you can change the order of stuff.
Exactly. That's
right.
Okay. So we change the order. This is actually the same now as using VERBOSE. But I figured you will handle it, so I didn't jump there. Okay.
I appreciate the faith.
Yeah. Okay, so 3 dots.
That's 3 anything.
Yeah. So in our case, that's gonna be
A, B, C.
Right.
That's gonna be the first one anyway.
And it's replaced by
X.
Okay. And the result is?
Okay, so it replaces all 3 of 3 anythings.
Yes, so it will do it repeatedly.
Right, yes.
Okay. You can limit the number of repetitions with the count equals something parameter. Mm-hmm. But by default, it will do any non-overlapping matches. Okay?
Okay.
Okay, so what will this match in our case?
That should be A and then B.
Right. and they will go in dollar.
So A goes into 1 \1 and then B goes into \2.
Right. So what does it do?
Swaps them over.
Yeah, swaps them over every 2 characters.
Ah, right, because it keeps on going. Yes.
And here too, I can limit if I want. And the F at the end, just to notice, it's just there. It remains
because
there.
It's alone.
Yes, because it was an odd number of characters. So there it was no match, so nothing happened. Okay.
Yeah.
Yeah, I think this went. We can skip this one. That's not that very interesting. I think we actually covered them already. These examples. Okay, so I had this example, another example. Let me just yeah, we are here fixing dates, and we have a couple of more, so we can finish it now, right? Okay. It's gonna be still long, but yeah. So this was some place where I had these dates. They look like this. Okay, so sometimes they looked like this. Sometimes they looked like this, with a 0 preceding the 1-digit months. Sometimes the 0 preceded the 1-digit letter. And I wanted to unify them. So always 4-digit year, always 2-digit months, always 2-digit day. Okay, so I needed a regular expression, a substitution that can do this. And what we have here is basically a test case for it. So I wrote down a couple of examples of input, what I expect to be the output. Okay, here is the actually code, the fixed date. And then what I do is go over the sorted list. Doesn't really matter that it's sorted, the keys. This is the original. I call the fixed date with the original, get the result, and then I compare the result with the value from the date's original. Okay, so now I need to explain finally what assert is. Assert is basically saying that, I don't know, what does assert mean in English? I have no idea.
I mean,
something that makes sure that this is right. Assume.
Yeah, assertion, yeah.
Yeah. So basically this expression says that if what it does, that if this thing is true, then the assert just says, okay, go on, next statement. But if this statement is false, then the assertion raises an exception and your program stops running. That's basically what assert does. And I'm not sure how often it's used actually in regular programs outside of tests. But in tests, definitely it's a good use. And so this basically will stop the first time the function misbehaves, or that the test case is incorrect. And then it's just printing out the values, nothing there. Okay. So how does this look like? Well, here is the \b. So we match a dash, we match a digit, and then end of word. Why do we need this end of word?
Not sure.
So it won't match the digit 0 here. So the \d won't match this 0.
All right, because you're only looking for one digit.
Yeah, so this one doesn't need to be fixed.
Yes.
What basically I do here is if there is a dash and a single digit,
then replace it with
add the
0
in front of it. Okay, but I don't want to match this one where I have a dash and a single and this digit.
Right. Yes.
Okay.
Okay.
So I want to make sure that afterwards I have either a dash or the end of the string. And luckily, the backslash B exactly helps with that.
Yeah, okay.
Okay?
And it will leave the 15 alone as well.
Sorry?
And it will leave the last row, like the 15
Right,
alone.
yeah, because
it's double
B
digit.
match the 1, but because of the B,
Yeah,
it can't
okay.
match. Okay. Yeah. Okay, so I have this string, and I would like to double the numbers. So what does doubling mean? Well, the first one is this one. Every time we match a digit, put it 2 of them.
Yeah, okay.
You will get this is 1 1 string with 3 3 numbers 3 4 3 4. But that's just one way to double the digits. The other way would be choose to multiply them with 2, right? But how can I do this? This is only string based. Everything here is string based. Nothing computation. Nothing.
So you need to change it to integers.
Not only that, I need to do some computation.
Yeah.
Okay. So there is some super extra fun thing in regular expressions that, and I used it a lambda, but don't worry about it. So instead of the string here, so this is a string, right? The replacement string. But instead of the replacement string, I can put there a function.
Right.
It can be just a function I defined outside. Okay, so I define a function and I just put it here. Or I can create it on the fly with this lambda expression. So what it does is this is a function that gets a single string, which is the match object. And then the expression here, whatever the expression is, that's what will be the replacement. So now I can do anything. Okay, I got a match, and on every iteration and every match, because there are multiple, right? It will do on every match in the string, it will call this function. And this function will, from the match object, this is the same match object that we had.
Right.
You get the group 0, which is the current full match, which is every time the current digit. Currently, whatever this matches. So think about it as calling the same match multiple times in several sections of the string. Okay, and this is how I get the actual match, which is the current digit or current number.
Yeah.
It's convert it into int, multiply it with 2, convert back to string, and that's what we need. And then it replaces, and now I get the doubles.
Right. Okay.
Okay. Don't worry about it. I think I wrote Python 8 years before I actually needed this and encountered this. I used it in Perl several times beforehand, but in Python I didn't. So, but when you need it, it's really, really powerful. Okay, so what else do we have here? Remove spaces, not that interesting. So this is something that, for example, in Perl, you would do in regular expressions, but in Python, you have the L strip, R strip, and just the strip to remove spaces from a string.
Yeah.
Okay, so that's the reason it's here. Nothing to do with regular expression. It's just because as I was converting some of the slides, I said, okay, so now this is a, okay, I'll go over this, even though it has nothing to do with bioinformatics. So this is a language, this looks like a language which is called the assembler. Okay, this is a really, really low-level programming language. Okay, basically this is how, these are instructions to the actual CPU. And I was shown this example at one of the companies that is making chips, that they have this code, and these are variables basically, A and R3, or actually A and B are variables and R R2 and R1, and all these they're also called registers. And which is sort of like a variable. And this just says move the value from A to R3. But that's not really interesting for us. What's interesting for us is that they made some design change. And so they had to replace R3 with R. So R1 with R2, R2 with R3, and R3 with R1. So just move them around because they changed the wires in there. I have no idea. So how can you do this? And you can't replace R1 by R2 in this text because then you won't be able to decide. You won't be able to know what is the old R2 and what that you still need to replace and what is the new. So one way to do is that to convert from R1 to R4. And then R2, then R2 to R, then you can, so it's a temporary string. And they did this and they put it on the chip and it burned down. And then they looked at that and then said, oh, but we used to have an R4 as well. So now it's gone. Okay, so then they came up with it's a better solution that, okay, now you just use some totally different string for temporary, which is better. But it would be actually even better if we could create a mapping that's easier, that maps them directly. So this is basically what we had in code earlier. Just match, replace R1 with R4, R3 with R, so just one, and then at the end R4 with R2. The trouble was that they also had R4 and they just forgot about it. Okay, so wait a second. Yeah, so this is the better solution where we have a mapping of which is I just call the variable mapping. It's called R1 goes to R2, R2 to R3, and R3 to R1. And then the regular expression looks like this. Okay, so what is in this regular expression? It's
So find either 1, 2, or 3 after an R that is after the edge and before the edge of the word.
yes.
Word
Okay.
or the string.
Why do we need the edges of the words?
So they would find it even if it's the first or the second.
So it won't match this one.
Oh, right. Or the one below. Okay.
Yeah, yeah, exactly. So because they had all these R12 and R, okay, I just made them up, but
yeah, no, fair.
this problem, okay? Because in the future they might get there. Okay, so now we match the R something, and do I need this? I'm not even sure. I'm not sure if I need the function here. Oh yeah, I do. I need. Yeah, sure, I need. So I needed the function here because I couldn't use the \1 as part of the Python code. So I could use the \1 in the replacement, but only if it's a string.
Okay.
I can't use it in the outside world. So that's why I needed a function here. And then in the function, I have the match object with group 1, which is the current R something. And then I just look it up in the mapping. So this match something is R1, R2, or R3. And then these ones.
So that's the key, yeah.
With the mapping is the other one. And then I just run this substitute on the whole thing at once, and it will do the whole work. So far it's good, right? So now it's improved. Yeah, we have this mapping. So what happens if I have more of these? So the R12 and R21 I also would like to do. So I would like to change these as well. Okay, now I can't use this kind of regular expression anymore because they're not single digits.
Yeah.
So I had to change the regular expression to be in parentheses and these pipelines. So this is going to match either R1 or R2 or R3 or R12.
But it doesn't match R21.
Yeah, but I missed that, yeah.
Okay, oh, right.
Okay, so I have the mapping for everything, but yeah. So if I wanted to also replace the R21, then I would have to add that one as well. So like this.
Right.
Yeah, but it's boring. Wait a second, where is it? Okay, no, this one. Okay, right. Yeah, now I just remembered. So what's the problem here? Well, you pointed out the problem, that I missed the R21. But what is the solution? The solution would be either to add the R21 here, but that solves this problem for now.
Yeah, but what if there are other?
But now we have you remember that I say dry? Yeah, and now the problem is that we repeat the two things here. Both here and here I needed the same thing. So let's eliminate this duplication. And that's what we have in the next slide, or next example here. So what we have here is now that we are going to create this regular expression automatically from this mapping. And then we only need to create the mapping, and the regular expression will automatically be generated.
Right.
So we just take the keys from this dictionary, join them together exactly as you said with the list.
With the pipes.
Ask me about the list.
Yes.
With the pipeline. Okay. And then we combine that with the \b opening parentheses and the closing parentheses \b. In order to get a regular expression that looks like this, but that contains all the keys from this dictionary. And the rest is the same. Okay, so are you okay?
Yeah, okay. No, I was processing for a second, but yes. Okay. I'm good.
Okay, so this is just basically what you asked a couple of slides earlier. If you can combine a list, well, the keys it returns a list, and we are combining them with a pipeline, and that's exactly what we got. Okay, so yeah, it's the advanced part of the regular expressions. Well, actually not, because we don't have the slides here for the beginning course, but there could be another 2 hours of talking about the advanced part of regular expressions. Okay, but that's just basically most of the time what people use so far. So this is just an example. This is the full example of the previous one, where it reads the file and then does the replacement and saves the file again. Okay, no, not that interesting for now. Okay, one other thing that can be interesting in the evolution of this screen is that you could put this mapping into an Excel file and read the mapping from an Excel file. And then you totally separated the code from the data, which is a lot of times it's good, because then you can give it the data to someone who doesn't understand programming. They only need to handle an Excel file. And then so just think about your lab that maybe some people don't know programming, and you don't want to give them a file because they will put the comma in the wrong place and then nothing will work. In the good case, in the bad case, something will work, but incorrectly. But if it's from an Excel file, well, then it's an input for you, and you can verify that the data looks correct and so on. Okay. There is this file type, which is more or less, but there's a file type called ini file or config file, where they have these sections, and in the sections you have these key value pairs. It's just text. And I would like to read this file, this text, and split it basically and get these two values. So I basically would like to split wherever I have this, which the normal split can't do. It can only split according to one single equal sign, but I can use R strip. Sorry, I can use this
Right.
on the regular expressions. I'm getting tired too much of this session. I'm sure that you are getting tired even more. Okay, so the R here it just removing the new line from the end, and then I use the RE.split, where I give it a regular expression and a string. And this is sort of works the opposite way from the search, because what it does, it matches things and then throws them away. It doesn't care about them. And whatever is between them, those are the interesting pieces. Those are the valuable pieces. And those are going to be returned here as a list, I think, or tuple or whatever. Okay, and then you can assign them, because in this case, I knew that there are going to be two, so I assigned them just to two variables.
Otherwise, it would be a list of stuff.
Okay, of two in this case, but you can, if you have multiple of these things that you need to split on, then it's going to be multiple elements. Okay, so now it made the split a lot more flexible, because the regular expression said, well, spaces, more or 0 or more, then an equal sign, then more spaces or not. Okay, so this will match this as well and everything here. Okay, and then I'm just printing them out in a similar way. Whew. Okay, we arrived to the exercises. There are quite a few exercises here. So this is like a lot of small ones. You have some skeleton here that you can use, skeleton program that you can use. Just try to maybe you don't have it the queue, so look for something else, pick some text from somewhere. You can run it on the source code of some other example. Okay, so more of these, so this is, well, match something that looks like a hexadecimal or an octal or a binary or a decimal number. And then it's just to play with that. So it's a non-negative, and then you start making it more complex. So at one point you would like to match stuff like this. Okay. That's another example. So there is something called an SNMP number. An SNMP number is basically a number with multiple numbers. So it's a string, basically. We call it an SNMP number, but it's a string. Okay, with that looks like this. So a bunch of numbers separated with dots. Okay, actually this in old, really, I mean, it's a menu system. Think about it, a menu system. So this is the in the first menu item, and then in there the second menu item, in there the seventh menu item, and so on. You can think about that way. Yeah, in a case of a hierarchy, it can be useful. Okay, but it's just used for all kind of places, and we need to sort them. But not just simply sort them, but make the decision first based on the first number, not the first digit, the first number. And if they are equal, then try the second numbers. And if they are equal, then try the third one, and so on. Okay, so you will have to compare them number-wise, these pieces. This is an exercise that I used to write down how much time does it take to give the presentations when I gave this course, or long time ago, when I started from 9 a.m. and finished at 5:30. Wow, long time. And we had this part, like apparently I started 9:20 here. I don't know. And then we had exercise starting. So these are the starting times of these things. And I would like you to create, first of all, something that looks like this. So start time, end time. And then a report that gives this. Okay, so how much time we spent on breaks, how much on dictionaries, how much on lists. Okay. It's just another exercise to do, to analyze some data here and then combine them. Then there are those ini files that I mentioned. So these are sort of standard configuration files for Windows usually, but it can be used anywhere. And there are modules for this. So normally you wouldn't write your own parser for this, but it's a good exercise. So this looks like this. This is a command. This is a section. And then there can be sections. And in each section, you can have key values. And the same key can be in separate sections with different values. Okay? Yeah, X-Wing and London. Okay, so whatever. And basically, I would like that you read it into a dictionary of dictionaries. So this is the key of the main dictionary. And inside, this one is a key, and this one is a key, and this is a value. So it's basically a two-dimensional dictionary, right?
Okay.
Okay, and then we can. So that's basically. This is the replacing Python with Java or whatever. Yeah. Here we have the phone numbers that I showed you at the beginning. So you can try to extract the phone numbers from here. I don't have the credit card numbers.
Probably better.
Yeah, it would be more
motivating.
Yeah. Anyway, so you have plenty of exercises. Enjoy them. If you have questions, do you still have any questions now, or?
Not now, but I'm sure I'll
Good.
have some.
So thank you for taking part and asking questions. And thank you everyone who watched this, and go ahead and enjoy the exercises. See you next video.
See you.